This is the third video in my series of videos on Georg Cantor's contributions to the founding of the theory of transfinite numbers. So in the previous video we looked at the first part of the first article published in 1895, which covered things like definitions of general aggregates and cardinal numbers. So in this video I'm going to continue with the first article, but here we're going to be looking at mostly simply ordered aggregates and ordinal types. By the end of this video we should be at the end of that first article, and in the next video I'll be moving on to the second article published in 1897. As in the previous video, there's not much in the way of theorems and proofs in this particular article. There are a couple of big theorems, one of which I'm going to go through, but mostly it's focused on definitions and basic concepts. So we're going to start off with this video with the definition of a simply ordered aggregate. So let's start out with some basic definitions, terminology and concepts. We're going to start out with the definition of simply ordered aggregate. We will only be dealing with simply ordered aggregates for this video. So sometimes I might just say ordered aggregate, and it means, at least in this video, exactly the same thing as simply ordered aggregate. So if M is an aggregate as defined right at the start of my previous video, then M is a simply ordered aggregate if given any two different elements, M1 and M2, of M, we can say that either M1 precedes M2, or equivalently M2 follows M1, or we can say M2 precedes M1, or equivalently M1 follows M2. Notice the terminology that I'm using here. I'm saying that M1 precedes M2, or M2 follows M1. So this symbol, although it bears a strong resemblance to the less than symbol, and this, looking at the other direction, the greater than symbol, that's this doesn't necessarily have anything to do with magnitude, or greater than or less than in the usual sense, usual everyday sense. These orders can be defined between elements that don't have anything anything akin to a numerical magnitudes. They might not even be numbers that are involved here. So we've got to be very careful how we interpret this symbol and the terminology that we use when we're referring to such a relationship. Having said that, sometimes on some aggregates the ordering, the simple order, might be determined by the magnitudes of the actual elements, particularly if you've got numerical elements. So if we take the aggregate R, which is the aggregate of all rational numbers greater than 0 but less than 1, then we can say that P1 over Q1 precedes P2 over Q2 if and only if P1 over Q1 is less than P2 over Q2. So this is the usual conventional natural ordering of the rational numbers between 0 and 1, and from this we can determine a simple order and make R into a simply ordered aggregate. On the other hand, we could define R0, which is an aggregate which has the same elements as R. So it's the aggregate of rational numbers greater than 0 but less than 1, but this time we define a different order on it. So P1 over Q1 precedes P2 over Q2 if and only if these are satisfied. So in other words, if P1 plus Q1 is less than P2 plus Q2, but if they happen to be equal, then we do go to the natural ordering. But notice in this case the simple order is determined completely by the natural order. Here it's only kind of partially determined by the natural order of the rational numbers. And we could define orderings that have nothing to do with natural orders or magnitudes or anything like that, full stop. But the reason that I picked this one out is because this particular aggregate plays an important role further down the line its order type, as we'll see, or ordinal type should I say, is a very specific type, a very useful type. So this will come into play later in the video. Okay, and once we've got a simply ordered aggregate, then we can start to talk about ordinal type. So here I'm going to quote straight from Cantor the definition of ordinal type. So every ordered aggregate M has a definite ordinal type, or more shortly a definite type, which we will denote by M bar. And by this we understand the general concept which results from M if we only abstract from the nature of the elements lowercase m and retain the order of precedence among them. Thus the ordinal type M bar is itself an ordered aggregate whose elements are units which have the same order of precedence amongst one another as the corresponding elements of M from which they are derived by abstraction. So what we see is something like this, the arrows representing this abstraction process. So we start with a simply ordered aggregate M, and we abstract from the nature of the elements. So now, if you think back to the previous video, we had M, and through a double level of abstraction we ended up getting to this M double bar, which was the cardinal number. But it also turned out that M bar was kind of the intermediate stage to get from M to M double bar. So I kind of explained this in the last video, but just to kind of recap that, what's going on here is we're starting with our aggregate of elements and it's got an order defined on it, but we take away, we abstract from the nature of those elements. So whatever they are, whether they're names of countries, whether they're numbers, vectors, functions, we don't really know, we don't really need to know. We just take away all of that information, and what we end up with at this stage is an aggregate that is just composed of general units, the most general type of unit. But it's still got the same order as this thing here. So in that respect they're identical in terms of their order. They differ only in how we view the units. So here we can see the nature of the units. Here we just see general units, almost like they're placeholders in which we can actually start to place specific units, specific elements. Okay, and then we can talk about similarity of aggregates. So two aggregates M and N are similar if and only if we've got a one-to-one correspondence between the elements of M and N. So this is quite similar to when we talked about equivalence of aggregates in the previous video. We've got this one-to-one correspondence between the elements of M and the elements of N. So let's suppose that the element M1 of M corresponds to the element N1 and M2 corresponds to N2. Well, what we also require from this one-to-one correspondence is that it preserves the order relations. So M1 precedes M2 in M if and only if N1 precedes N2 in N. The orders here, even though I'm using the same symbol, they're orders defined on different aggregates, so they're not the same relation. They're different relations defined on different aggregates, but the order of precedence is preserved through this one-to-one correspondence here. Such a one-to-one correspondence is called an imaging. An imaging of the aggregates M and N onto one another. And these are going to play a crucial role in what's to come in the rest of this video. Some consequences of this. So if M is similar to N, this is if and only if the ordinal type of M is equal to the ordinal type of N. So notice here the difference in symbol that I use between the m and the n, the m bar and the n bar, they are aggregates. But this is, to me, quite significant because this is indicating really that when I go through this first level of abstraction, from m to m bar and n to n bar, they're ordinal types, then I actually get funneled into the same aggregates at this point. So it's not that m bar and n bar are just merely similar aggregates, they are actually one and the same aggregates. And it's really worth emphasizing that ordinal types themselves are aggregates, and I get exactly the same aggregate. And this is quite similar to what we saw with equivalence. So if we had, for example, m is equivalent to n, this is if and only if m double bar is equal to n double bar. So these are the cardinal numbers. So this double level of abstraction also funnels us into the same aggregate, but in this case after two levels of abstraction, here just after a single level of abstraction. And it follows that if m is similar to n, then m is equivalent to n, but not conversely. So this is quite significant because it means that two aggregates that are equivalent and therefore have the same cardinal number might actually have very different ordinal types. So we can subsume under a single cardinal number potentially many different ordinal types, a huge number, an infinite number of different ordinal types, potentially, depending on the particular cardinal number that we're dealing with. So I just want to make a couple of remarks now on notation. And I'm just going to complete this chain here. So as we know, starting with an aggregate, we go through one level of abstraction to get to the ordinal type, two levels of abstraction to get the cardinal number. However, don't be tempted necessarily to feel that the number of bars here is indicative of the number of levels of abstraction that we've actually gone through to get to that particular stage, because very often we will use lowercase Greek letters to indicate ordinal types. So we might say, for example, that m bar, the ordinal type of m, we might actually denote it by alpha or beta or whatever, some lowercase Greek letter. So if I abstract another level from this, I get m double bar. But if I abstract another level from this, I just get alpha bar. And alpha bar is the cardinal number of alpha, but it's also equal to n double bar, the cardinal number of the original aggregate. So here, the number of bars doesn't bear any resemblance to the number of levels of abstraction that I've gone through. So if I call m bar alpha, there's already this has already gone through that first level of abstraction potentially, but we are just referring to the aggregate that is the ordinal type of m. It might not have gone through a level of abstraction. We're just talking about that particular aggregate. So we can't go through that first level of abstraction again, or there'd be no point in doing so. We can, if we go through another level of abstraction, we've got to go through to get to the cardinal number. So as I was saying in the previous video that I made, Cantor's notation can be sometimes a bit more fluid than we might expect from modern day kind of textbooks and treatments of this kind of thing. Really to determine what is exactly meant by a particular notation in Cantor's work really has to be deduced from the specific context in which it appears in some cases. Obviously there is some kind of consistency there with the notation. It's not just completely ad hoc or random, there is some consistency there, but sometimes similar things can be used, can mean different things in different contexts. So you've really got to be on your toes a little bit with that. So that finishes up with the basic definitions and terminology. We're going to have a look now at finite and transfinite ordinal types. Let's have a quick look now at finite and transfinite ordinal types. So in the previous video we defined finite and transfinite aggregates as being those aggregates which have a finite cardinal number or a transfinite cardinal number respectively. So if we take M to be a simply ordered finite aggregate, so it's finite and simply ordered, then obviously it's got a finite cardinal number, but it will also have an ordinal type. With it being a simply ordered aggregate, it's got an ordinal type. Well, naturally we call such an ordinal type finite as well. Okay. And also we denoted the finite cardinal numbers as 1, 2, 3, 4, new, etc. Well, it turns out that with finite ordinal types, that there is basically only one of each finite ordinal type. So just like I was saying earlier in the video, under a single cardinal number we can subsume potentially many different ordinal types, potentially an infinite number of them. Well, in the case of finite cardinal numbers, there is only one ordinal type in each corresponding to each cardinal number, and therefore we use the symbols 1, 2, 3, 4, new, etc. to represent the finite ordinal types as well. There aren't any other finite ordinal types other than the ones that correspond to the finite cardinal numbers. So we use these symbols for both cardinal numbers and ordinal types of a finite nature. And it doesn't really give rise to any confusion, despite the fact that obviously ordinal types and cardinal numbers are very different objects. They're aggregates, but they are very different objects in and of themselves, but it doesn't really give rise to any confusion. So what we can say is that any two finite aggregates, finite simply ordered aggregates that have the same cardinal number must actually be similar. So if M and N are finite and simply ordered aggregates, then if M double bar is equal to N double bar, then actually we get that M bar is equal to N bar, which of course means that M is similar to N, which in general is not the case. Normally we can't do this, we can't go in that particular direction. We can't say that if two aggregates are equivalent that they must be similar, but we can do in the finite case. So there's no, there's very limited behaviour really with these ordinal types, with these finite ordinal types. So there's not really that much of interest to us. It's really the transfinite ordinal types that we're interested in. So naturally enough, any aggregate that is transfinite gives rise to a transfinite ordinal type. So M transfinite, again simply ordered aggregate, then it's transfinite by definition if its cardinal number is transfinite. And naturally, if it's a simply ordered aggregate, it gives rise to M bar, an ordinal type, which itself is defined to be transfinite ordinal type. Now in this case, it is very possible for us to have two different aggregates of the same, two transfinite aggregates of the same cardinal number, but with very different ordinal types. So all of the aggregates of all of the transfinite aggregates having the same cardinal number but different ordinal types, we can gather all of their ordinal types together into what's called a class of types. So if, for example, we take all of the transfinite aggregates with cardinal number A, then we represent by A with square brackets around it the class of types corresponding to this cardinal number. Okay, so in this class, which itself is an aggregate, are all of the different ordinal types that have the same cardinal number. So in the case of transfinite cardinal numbers, there's going to be probably an infinite number of these in there. With it being an aggregate, it has a cardinal number. So we can find its cardinal number going through this double level of abstraction, and let's denote its cardinal number as A primed. Well, it turns out then that A primed is a cardinal number that is not equal to the cardinal number A. And in fact, it turns out that A primed is greater than A. And this is true for any transfinite cardinal A. The class of types corresponding to that cardinal number has itself a cardinal number that is greater than A. So A primed is greater than A. In particular, we're going to be interested in the class of types corresponding to Aleph naught. So this is going to be one of the main. This is going to be the main focus of attention for quite a significant part of the development of these transfinite numbers in Cantor's work. So that's a basic introduction to finite and transfinite ordinal types. Notice that we're talking about ordinal types here. We don't know, when it comes on to transfinite ordinal types, whether they are actually numbers in a certain sense. So when it comes to finite ordinal types, we can kind of associate them with the numbers, with the cardinal numbers 1, 2, 3, 4, etc. So they are numbers in a certain sense. But with the transfinite case, yes, there are some ordinal types that we will eventually start to call ordinal numbers, but not every ordinal type is an ordinal number. We need to figure out which are the ones that really behave like numbers, that allow us to do perform kind of arithmetical operations on in a meaningful way. So for the time being, we're still stuck with this terminology, ordinal types. Okay, so I'm going to move on to the next section now. Let's have a look now at the inverse of an aggregate. So if we've got M, which is a simply ordered aggregate, finite or transfinite, doesn't make any difference, such that the elements M1 and M2 in M are such that M1 precedes M2, then if we for each such pairing of elements, if we switch them around, so we leave this symbol the same but we just interchange their roles, such that M2 now precedes M1, if and only if M1 precedes M2 in M, then we get the same aggregate of elements, but it's got a different ordering now placed on it. So we're going to indicate that by writing M star. So the star just indicates that it's got some relation to M in terms of its order. But I emphasize it's still the same aggregate of elements. So this is the inverse aggregate of M. So if the ordinal type of M, since it was assumed to be a simply ordered aggregate, if its ordinal type was equal to alpha, then we'll denote the ordinal type of M star to be alpha star. Okay, and it may be that alpha star is a completely different ordinal type to alpha. It might be that in some cases alpha star is the same ordinal type of alpha. It really depends on the ordinal type that we're working with and the aggregates that we're working with. So there's all sorts of behaviors that we could get with this. But as a specific example, omega, which equals the order type of E, ordinal type of E, sorry, which equals E1, E2, E nu. So it's the ordinal type of this aggregate in such a way that E nu precedes E nu plus 1 for all nu. Then the inverse of this is going to be omega star, which is the ordinal type of E star, which it's the same aggregate of the same elements, E2, E nu, etc. And it's the ordinal type of this aggregate, but in such a way that E nu plus 1 is precedes E nu in this case. So we can almost view this as kind of an ascending aggregate. The order, the simple order, we can visualize as kind of an ascending order of elements. Here it's more of a descending order of elements, so coming in from this direction maybe. Okay, it's worth pointing out at this stage as well that two similar aggregates, in other words, aggregates with the same order type, ordinal type, I keep saying order type, but I mean ordinal type, can be possibly imaged onto one another in a single way or possibly many different ways. So just by the fact that they have the same ordinal type doesn't mean that there is just a single possible imaging of the two aggregates onto one another. And in particular, an aggregate can be, a simply ordered aggregate can be imaged onto itself. And this can happen in at least one way, the obvious way where we just keep correspond to each element itself in the second copy of that particular aggregate. But it might be the case that an aggregate, a simply ordered aggregate, can be imaged onto itself in many different ways. So in the case of E here, or even E star, these can be imaged onto themselves in only a single way. So if I've got two copies of E, then the only way that I can image E onto the second copy of itself is to take each element to exactly the same element. So it's basically the an identity function or something like that. So I'd have to map in both of these cases E nu to E nu. So these aggregates can only be mapped onto themselves, imaged onto themselves, sorry, in a single way. However, we've not done addition of ordinal types yet, but if we just consider the ordinal type omega star plus omega to be something along the lines of E minus nu, E minus 1, E naught, E1, E nu, etc. So it's the ordinal type of this aggregate. So this is kind of an aggregate. We could visualize this as kind of similar to the integers. I say similar, resembling the integers, maybe I should say, in such a way that E nu precedes E nu plus 1. Then there's an infinite number of ways that I could image this aggregate onto itself. So I could say, for example, E nu with E nu plus 1 for each nu. So I've got two copies of this aggregate. All I do with my imaging, this one-to-one correspondence, is kind of take each element from my first copy and just bump it up to the next element in the second copy. Or I could take E nu correspond with E nu plus sigma for any integer value of sigma, really. So this gives a one-to-one correspondence, an infinite number of one-to-one correspondences between this simply ordered aggregate and itself. So there's quite a lot of variety in behaviors that we can get, and there's not necessarily a single imaging that we can get. So this idea of an aggregate only being imaged onto itself in a single possible way is not something that's peculiar to just finite ordinal types, because these are transfinite ordinal types. So that's something that we actually see with transfinite ordinal types as well. It's just that with transfinite ordinal types, we get this possibility that an aggregate, a transfinite, simply ordered aggregate, can possibly, in some cases, be imaged onto itself in possibly infinitely many different ways. It really depends on the ordinal types that we're working with, not the specific aggregates, but their ordinal types. So that finishes up with this particular section. We're going to move on now to arithmetical operations of ordinal types, namely addition and multiplication. So let's have a look now at addition of ordinal types. So let's assume that we've got two aggregates, simply ordered aggregates, m and n, such that the ordinal type of m is alpha and the ordinal type of n is beta. Then we can form, this notation was introduced in the previous video, it's the union aggregate of m and n. So implicitly we are kind of assuming that m and n have no common elements. We can make this into a simply ordered aggregate under the following conditions. There might be other ways that we can do it, but this is one possible way, and it's the way that we're going to go with now. So m1 precedes m2 in the union aggregate if m1 precedes m2 in m. So in other words, if both m1 and m2 are elements of m, and m1 precedes m2 in m, then they precede, m1 precedes m2 in the union aggregate as well. Similarly for n1 and n2 in n, but also if we choose m from the element m from the aggregate m and the element n from the aggregate n, capital N, then m precedes n in the union aggregate if m is in n, m is in m and n is in n. And this establishes the union aggregate as a simply ordered aggregate. And then we can define, so it has an ordinal type. With it being a simply ordered aggregate, it's got an ordinal type. So we define alpha plus beta to be equal to the ordinal type of the union aggregate of m and n with this ordering defined. And alpha here is called the organd, and beta is called the addend. Okay, so it's fairly easy to show that addition of ordinal types satisfies the associative law, namely alpha plus beta plus gamma is equal to alpha plus beta plus gamma. But what fails is the commutative law. So this wasn't a problem with cardinal numbers, but it's certainly a problem when we come on to ordinal types. The commutativity of addition just doesn't follow. And we can see this fairly easily with the following example. So if we take the aggregate E, which equals E1, E2, E new, etc., then we know that the ordinal type of E is omega. So we saw that earlier in the video. Well, on the assumption, sorry, that E new precedes E new plus 1. Okay, so let's find, let's add another element into this aggregate E. So we get the union aggregate E F, which is E1, E2, what's it, E omega, E new, and then right on the end we've got F, this new element F. And we're also going to have Fe, so the other way around. So here F goes before the E1, E2, E new, etc. And with the obvious orderings as defined by this, so all of these E's will precede this F. Here F precedes all of the E's. And we're interested in the ordinal types of these. Well, from what we've defined up here, the ordinal type of this is going to be omega plus 1. And the ordinal type of this is going to be 1 plus omega. But it's fairly easy to see that we can image this aggregate onto this aggregate in a fairly obvious way. So E1 to F, E2 to E1, etc. E new will end up at the number before E new here. So it's kind of, in a way, all of these elements are mapped to the element before in this aggregate, in a way of speaking. However, if we now look at how could we image this onto this aggregate, actually we can't do that. Not and preserve. We can map the elements onto this in a one-to-one correspondence, but not in such a way that it preserves the order of the elements. So what we can see then is that 1 plus omega is equal to omega, because we've got the right kind of correspondence. But on the other hand, omega plus 1 is not equal to omega, because we can't get an imaging here. We can get a one-to-one correspondence, but not an imaging. So therefore, 1 plus omega, 1 plus omega is not equal to omega plus 1 in that case. So just with this simple case, we can see that the commutative property, the commutative law, fails for addition of ordinal types. So let's have a look now at multiplication of ordinal types. So let's have a look now at multiplication of ordinal types. So again, start off with m and n, simply ordered aggregates. Ordinal type of m is alpha, ordinal type of n is beta. We form a new aggregate s in such a way that to each element n in the aggregate n, we replace it with an aggregate m sub n, which is similar to m. So we remove the element n and replace it with basically an aggregate, or the elements of this aggregate. Naturally, mn being similar to m must be a simply ordered aggregate itself. And we'll assume that each of the mn that we choose, m sub n for each element of n, don't have any common elements. So then we need an ordering defined on S. So the ordering is going to be as follows, that m sub n1 precedes m sub n2 in S if these elements precede each other in the if they both belong to the same mn, and mn1 precedes mn2 in this kind of similar aggregate to m, this m sub n. On the other hand, if mn and mn primed are in S, but they're in different mn's, then mn precedes mn primed in S if n precedes n primed in n. And this establishes S as a simply ordered aggregate. And we can define alpha times beta to be equal to the ordinal type of the simply ordered aggregate S. And we get the usual associative property holding. So alpha dot beta dot gamma is equal to alpha dot beta dot gamma. No problems there. However, we've only got, relating to the distributive law, we've only got alpha dot beta plus gamma equals alpha dot beta plus alpha dot gamma. Something else that I need to mention as well is that alpha here is called the multiplicand, and beta is called the multiplier in this product here. The distributive law does not hold the other way round. So if I made alpha the multiplier and beta plus gamma the multiplicand, the distributive law would not hold. So effectively, you can imagine this as, think of this as maybe left distributivity, something like that. And also we don't have the commutative law holding in general for multiplication of ordinal types, as the following will show. So for example, the ordinal type 2 dot omega will correspond to an aggregate roughly of this form, which is E1, F1, E2, F2, E3, F3, etc. Okay, and clearly this has the same, this should be an ordinal type. Clearly this has the same ordinal type as omega. But now if we look at omega times 2, then what we get is something that's more like E1, E2, but then we get F1, F2 up here. So effectively we get an infinite sequence here, and then that's followed by another infinite sequence that's effectively the same ordinal type, So this is definitely not equal to omega. There's no way that I could image this aggregate onto this aggregate here. So what we get then is that, so that is not equal to omega. So therefore 2 times omega is not equal to omega times 2. So that's a fairly simple example showing that the commutative law doesn't hold. So probably it's unlikely to hold for in many other cases as well. So that's multiplication of ordinal types. So I'm going to move on to the next section now.